So the central limit theorem formalizes what we saw in our discussion of sampling distributions. Right? First, as statistics, theorems, and procedures often do, it lays down some conditions. Right? If either the original population is normally distributed, or the original population isn't, and the sample size is greater than 30, then the sampling distribution of the sample means can be approximated by a normal distribution. Oh, now that's an incredibly useful statement right there. What that says is that everything we already know about normal distributions can be applied to answering questions about sampling distributions. That is, answering questions about the probability of the average value of a sample of a certain size. Okay, regardless of the underlying distribution, it doesn't matter how the population itself is structured. If the sample size is large enough, then we can use all of our normal distribution calculation methods. Right? Now this next part states what we already saw in our sampling distribution example. The mean is the same, right? The mean of the sampling distribution is the same as the mean of the underlying population. And this last part is the only significant difference. When we're dealing with groups instead of individuals, we have to adjust the standard deviation by dividing it by the square root of the sample size. So I've kind of outlined two scenarios here, right? Two scenarios that you have to kind of have firmly in your head, right? In the first one, if you're being asked about an individual member, one person, one package, one machine part from a normally distributed population, then you use the methods we've been talking about in the previous lectures in this chapter. If you're asked about a mean, right, I want to emphasize that part right there. This does not apply to anything except a mean. We're going to talk about proportions in the next lecture. If you're asked about the mean of a sample or a group, then you do two things. First, you check to make sure the requirements of the central limit theorem are met. That's that the population is normal or the sample size is greater than 30. And if they are, then use the population mean for the mean and make this adjustment to the standard deviation. All right, so let's look at two examples, right? Two scenarios here that are going to illustrate those two cases. Right? In the first one, I give you information about the mean weight of an 18-year-old, so 156.5 pounds, and there's a standard deviation of 26.5 pounds. My question is, what's the probability that a randomly selected male has a weight less than 140 pounds? Okay, I've put in bold the key phrase here. A randomly selected male. We are talking about a single person. Right? Because we're talking about a single person, I'm going to do what we did in the previous sections in the previous lectures. I'm going to calculate the z-score. Right? That's going to be 140 minus 156.5 divided by the standard deviation. That's 26.5, and that is negative 0.62. Then I know that the probability that x is less than 140, right? That's what I was asked about. A weight less than 140 pounds is equal to the probability that z is less than negative 0.62. Now, you go to your table or Excel, your calculator, whatever software computer you use. This is 0.267. All right, so that is scenario one. Right, now, this next one, right, the setup is the same. I'm told the mean weight of an 18-year-old male. I'm told the standard deviation of that population. But now I'm asked about the probability that a randomly selected sample of 20 males. Now I'm talking about a group. All right, this is a central limit theorem. Central limit theorem situation. First, we're going to confirm the requirements. We're talking about weights. Weights, generally speaking, like many physical properties, are going to be normally distributed. All right, so we don't have to worry about the sample size, right? So now what are we going to do, right? We're really going to walk through the same process again, but notice I'm going to do a little new notation here. The mean of the sampling distribution, right? It's kind of like the average of the averages, right? This is still 156.5. That doesn't change. The standard deviation of the sample means, this is going to change. This is 26.5, that's the original standard deviation, divided by the square root of the sample size. And according to my calculator, this is 5.926. Quite a bit smaller, right? And that's what we expect to happen with these questions. Okay, so now, what am I going to do? I'm going to calculate a z-score, right? My z-score is 140 minus 156.5 divided by my adjusted standard deviation, 5.926. And again, I'm going to go to my calculator. This is negative 2.80121. And again, that's what I expected, right? The denominator of my z-score formula got smaller, so I expect this to be bigger, or in this case, more negative. Okay, now I can answer my question. I'm asked, what is the probability that the sample mean is less than, what was it? It was 140 still. And this is equal to the probability that z, and it really is just z, right? A z-score is a z-score regardless of which method we're using, is less than negative 2.80121. You go to wherever you like to look up these probabilities. This is 0.00255. Right, so those are our two cases that we have to work with here. All right, so let me give you one. All right, you can pause if you like. See if you can work this one out. See what you come up with. Then we'll go through it together. Okay, so we're looking at a group of people, right? We're talking about 36 adult females, right? So I'm thinking central limit theorem situation, right? What are we talking about? We're talking about overhead reach distances, but that's more or less the length of your arm, right? And just like in the last example, we kind of expect physical properties to be normally distributed, but even if it wasn't, even if there was something weird about this particular measurement, we're still okay because our sample size is greater than that 30-person threshold, right? So now we're in our calculations. I'm looking for the probability that the average reach of this group is less than 205. So my mean is going to be the same as the populations. It's going to be 205.5. And my standard deviation I have to adjust. It's 8.6 divided by the square root of 36, which according to my calculator is 1.433. Now I can get my z-score. My z-score is, just don't make sure I get these in the right order. Right, I always mix these up sometimes. It's going to be 205. That's our, that's the value we're given here, minus the mean. That's 205.5 divided by my adjusted standard deviation, 1.433. And that is negative 0.34884. So my probability here, this is the same as the probability that z is less than negative 0.34884. And Excel is actually what I usually use to do these. Excel tells me that this is 0.364. And that's it. All right, that's my probability. All right, so I've got one more example here, and this is a very practical one, right? We have an airplane, small airplane, and I know how many passengers it can carry, and I know what the total weight allowance of this plane is, right? So what I want to talk about, is since the plane is full and all passengers are male, given what I know, right, about the mean weight, the standard deviation here of adult men, should I be concerned, right? What's the probability that the aircraft is overloaded? Okay, well here's my first thought, right? If the plane can carry, I got to talk about averages, right? When we're talking about a group. So if the plane can carry 6,200 pounds, and that's spread over 37 passengers, then the average weight of a passenger is going to be 6,200 divided by 37. This is 167.5676. So what I want to know is, what is the probability that the average weight of a group of this size is greater than 167.5676? If that number is even a small number there, it's going to maybe have me not getting on that plane. But let's see what we can figure out here. Okay. Our mean, the mean of our population, which is the same as the mean of our sampling distributions, is 182.9. The standard deviation is 40.8 divided by the square root of our sample size. That's the number of passengers. That's the square root of 37, which is 6.7075, right? Quite a bit smaller, which is what usually happens here. Okay, so what is my z-score? Right, my z-score is 167.5676 minus 182.9 over 6.7075, which according to my calculator is negative 2.28587. Okay, so I have to do this greater than probability, right? This is the same as the probability that z is greater than negative 2.28587, and our tables and most of the software really doesn't do greater than. So I'm going to treat this as a complement situation. This is 1 minus the probability that z is less than that z-score. And again, you go to your calculator, this is 0.989. There is no way I am getting on that plane, right? This is the probability that the aircraft is overloaded. And intuitively, this should be reasonable to you, right? Because look, if every passenger, right, there's 37 passengers, and if every passenger had that average male weight, 182.9, that would make our total weight 67.3, which is well over this tolerance, right? So I am simply not getting on that plane. Okay, so what's next? Well, we've got one more topic to cover with this idea of a central limit theorem. And it really is going to be the a practically identical calculation. We're just going to see how to do this if we're talking about a population proportion rather than a population mean. Again, the only thing is going to be different is the way we adjust the standard deviation.